So we have a great interest about electromagnetic counterparts from these systems. I'll also skip this slide. I'm pretty sure everyone has seen this figure a couple of times today. Okay. So in relativist...
Recording in progress.
In the relativist standard, binary black holes are the same. They all scales with the m. And running this binary black hole simulation in full GR, it's not the easiest thing, but it's not super hard these days. After 2 decades of numerical relativity, putting a matter and especially plasma around it, then it's a whole different story. You need to solve these MHD equations on top of the curved background, and sometimes this matter might try to back react to the evolution of the binary. And there has been a very impressive amount of effort from the theory community, as you would probably have seen for the last couple of days, has been put on solving this problem in a more realistic setup. So if you think about how this binary will evolve over time, in the in-spiral phase, especially in the closed-in spiral phase, where numerical relativity is worth, I would say, you have all these cool features like circumbinary disk, you have mini-disk around individual black holes, you have jets from this, and once this binary gets close enough, it gets decoupled from the binary, all this cool physics happening. In the moment of merger, I want to point out 2 very important general relativistic effects. First is the gravitational wave mass loss. So because you radiate the energy in the form of gravitational waves, this remnant actually loses about several % of mass. Yeah. And another important thing is, if your binary is asymmetric or individual components has spin, your remnant can pick up a linear momentum into one direction, which is called a gravitational wave kick or gravitational wave recoil. Yeah. And if you imagine you have this kind of merger happening in the circumbinary disk, and if the remnant picks up the recoil, we're trying to think about what kind of shocks or transients or jet activities that remnants might pick up as it flies through the circumbinary disk around it. Yeah. So yeah, I would say apart from all this cool binary simulation, I'm mostly working on the post-merger phase. Yeah. To me, it was easier because we only have one black hole. Yeah. So before moving into what we actually did, I did a transient GRMHD simulation solving these complex things, but if you just look at the equation here on the top of the corner, this is just a naive kinetic energy estimate. Suppose you have a 10 to the 8 solar mass black hole getting kicked up the typical recoil speed, which is 200 kilometers per second. And just for the information, the typical energy from the supernova is 10 to the 51 erg. This is actually a tremendous amount of kinetic energy that the black hole suddenly picks up. And it's actually no surprise that this object can have decent imprints it will leave on the surrounding environment. Yeah. I compiled some kind of list of the other impacts of recoil supermassive black hole. So I'm trying to convince everyone that it's really cool. Yeah. A lot of focus on the GRMHD part. Yeah. So we took there was a long, like hundreds of orbits of binary accretion simulation done by Caltech team 2 years ago. They basically find if you put the binary in the highly magnetized disk for a long time, they converge to something that called like a binary magnetically arrested state. It looks like a single black hole's magnetically arrested state, not exactly same. And this was actually not full GR simulation. This was Newtonian simulation putting 2 sync particles and putting 1 PN orbit around it. Yeah. And we take the snapshot from the very final moment of this simulation, and we put the black hole at the center, and we'll impose the kick. So it's not consistent in terms of this is not full GR, but we thought this might be enough for our current purpose here. So I'll just keep it simple. It took almost half a year to import this data into a relativistic simulation setup, but it's done. And this is like a side view and top view of the initial data ported into our simulation code, and we put the spinning black hole at the center, rescale all the variables properly, and we'll shoot the black hole into some different directions. Now, we have to choose consistent recoil velocity, because this is the value you get from general relativity. One practical difficulty over here is this scale, which I call the region of influence here, let's say your black hole is getting kicked with this velocity. This is roughly the region inside of which gas remains gravitationally bound to the black hole. Yeah. And this is the key length scale you probably want to resolve in your simulation box. The problem is it's really, really, really big compared to the horizon size. So we kind of had to compromise. We had to arbitrarily shoot black hole into like a really fast velocity and be very cautious of interpreting results. Yeah. So we chose this radius with the falling in this range. So it's not too large so that we can actually afford this computation, but it's big enough, at least more than 100 times the horizon size to keep this scale separation. So these are all the setups we considered in our simulation. We put shoot the black hole in 3 different angles with some combination of different velocity. This velocity might sound actually really fast, but disappointingly, this is the slowest wind speed accretion that has been on black hole accretion in our community so far. 0.1 c is the state of the quo, and people are trying to push this into a much more slower realistic velocity. Yeah. So this was the best we could do. Yeah. Okay, and let's just like look at how it looks like. So it's more like exploring what could happen depending on the kick angle. So early phase of the normal recoil will look like this. This is the snapshot that I looked from the more of a global picture, and that circle is the GM over V squared. Yeah, I'm showing it on top of this plot, and this is just zooming in the black hole. We're actually resolving horizon, solving full GRMHD equations here. So it's launching jet and getting ejected out from the disk. This dashed curve is, we're using this Bernoulli criterion to estimate which part of the disk will remain gravitationally bound to the black hole. This is not the perfect criterion for dynamic simulations, but it gives us a sense. Yeah. This is some time after that, so I annotated some obvious features that you can probably see. The black hole is getting shooted vertically upward. We have jet, we have this diffuse material and tightly bound accretion disk. And I'll call this like a mini AGN, and it preserves steady jet activity over time. And we expect this might cease its accretion activity after some time scale, roughly the mass divided by its accretion rate. And the next case is you shoot the black hole in 45 degrees from the accretion midplane. This is actually a very interesting case that you see this long streamer emerging from the original circumbinary disk getting into the black hole in the tilted angle. And this is the jet like about 40 degrees, 50 degrees misaligned with its original axis. You might think that black hole is spinning this way, but it's not. Black hole is actually spinning upward here. And I also wanted to bring this example. It's a really nice example that jets are not always aligned with the black hole's spin. It's really easy to steer them into a different direction by the accretion flow surrounding it at a larger scale. Okay, the next case is you shoot the black hole directly into the midplane. And here I'm showing the jet, and this is not the mass density. This column is showing the internal energy, so you can think this as a temperature. Yeah. So here the black hole is directly colliding with the circumbinary disk, and it has a copious shock heating producing it. So we expect that there's going to be bright thermal afterglow. Say the thermal emission might be strongest for this recoil angle. Yeah. And you actually see this configuration from the different perspective. We actually saw that behind the black hole, the magnetized cavity formed before the merger actually gets left behind and drifting downstream. A lot of active magnetic reconnections and heatings are happening here. So this might be actually functioning as an additional source of non-thermal emissions coming out from these systems. Okay, I'll put some results here, but just be careful that some of this morphology you just saw from the graphics might not be there if you actually push the velocity into realistic ones. So I'm trying to be very careful here interpreting the difference between these three cases. So if you eject the black hole 90 degrees from the midplane. I would say this is actually the cleanest case. The black hole just grabs material, travels out from it, and if we're lucky, we might see this object as something called the off-nuclear AGN. And for the 45 or oblique recoils, these are the things with the highest nonlinearity and variability. And for the direct in-plane recoil, this might also look like pretty smooth accretion activities, but with the very bright thermal afterglows. And yeah, I'll note several caveats here, but I would emphasize twice here again that picking a realistic speed is a game changer here. This is the best we could do, but I'm very eager to try with the even more slower one if we can actually afford this computation. Yeah. Now, this led to a fun little experiment that I did with Newtonian hydro. So if you think about this tilted disk onto the 45 degrees recoiled case, I was just trying to answer this question: what happens in the global scale? Yeah. So I just shot the black hole in the 45 degrees here, and actually it was possible to check that if your disk is big enough, it doesn't actually have to be orders of magnitude bigger. It's still okay to be like comparable, just a few times of this radius. An slight out-of-plane recoil, it can do, without that much difficulty, reorient the entire disk or even spin flip it. So this arrow is showing the angular momentum of this mass distribution after a long time. You can actually see that the z component is actually pointing downward. Yeah. So I'm trying to see if this can explain some of these warped features that we probably see from AGNs or reorientation of the jet after it merged. Yeah. So put this takeaway slide, but I'll just give a final pitch on this last point. The numbers you saw from here, the features, they might not be true, but the trend that we saw, I think is likely to be true. And we got a conclusion from here that the recoil velocity matters, but recoil angle relative to the circumbinary disk midplane also matters a lot. And if we can estimate the orbital inclination of the supermassive black hole binary before the merger, and we can determine this angle relative to the disk, looking from the EM afterglows, maybe this could be an interesting way to get some information about the merger environment. And that's it, and I'll have to take any questions.
That was so cool to see an actual recoiling black hole. It was slower than I thought it would be. Any questions? Come up and use the mic.
Yeah, awesome talk. The question about the jet orientation with respect to disk and stuff, it might have been a visualization thing or I don't know, but the jet seemed to be pointed like more aligned with the disk than away. And like in the opposite direction, I would assume pressure gradients would be in the system. So I was just wondering, like, what is aligning the jet here if it's not the black hole spin?
So if you actually look very close to the black hole, it's being launched along this spin axis, but it's steered by the angular momentum of the accretion disk here. Yeah. So it's actually aligned with the global angular momentum of the accretion flow here. Yeah.
Hi. I'm not a mic expert, so I'm just going to take this off so I don't go on my tiptoes. The great presentation, thank you. I was wondering, when you were talking about how the jet is reoriented, what angle, like, maybe you said I missed it, what angle is it reoriented? Is it like a full, like, flip, or is it related to some, like, parameter?
So I have to confess that I actually started this thing when I was trying to give an answer to that question that I had last fall. It's very sensitive to this ratio. That's my very preliminary conclusion I'm having from this Newtonian thing. It also depends on the mass density radial fall-off rate in your disk model, but not a lot. I would say the ratio between the actual size of the disk and GM over V squared this is actually governing how much angle you can actually do. Is like only 50 degrees, or can you completely flip it? And yeah, because like velocity plays like a decent role here. It's like, yeah, we better be really careful choosing this value.
Thank you.
Okay, last question. Next speaker can start coming up.
You said you weren't able to do kind of realistic recoil velocities. So I guess, what is the realistic recoil velocity? And then you said, I think it was 10% speed of light.
Yeah, so the fastest one you can ever get is about 5,000 kilometers per second. If you have like a spin into very specific configuration, typically if you're not extremely spinning, and you can typically get like several hundreds kilometers per second, but most extreme kicks are happening off-plane. Yeah, this is like interesting phenomenology you can get from NR simulation. So we actually need to be careful of choosing angle and velocity at the same time. Yeah.
And so the kick in these cases was, how did
Oh, here. So the other one. All the figures that I showed, the volume renderings are from like 0.05. Yeah.
All right, let's thank our speaker again.
Hello, everybody. My name is Michael Rizzo-Lopez. I'm a PhD candidate at Vanderbilt University, where I work with Kelly Holly Bockelman and Andrea Derdzinski. And today I'm going to be talking about processing eccentric binary black hole systems embedded in gaseous accretion disks. So first, the specific project that I'm currently working on studies how the binary black hole evolution can evolve when we introduce relativistic apsidal precession. We've seen a lot of really beautiful GRMHD simulations recently in the previous talk studying the late in-spiral phase, and we also saw a very awesome talk in the last session studying misaligned disks further out in binary separation. In this scenario, we're going to study specifically just before the actual gravitational wave in-spiral regime. So as many people have been saying, I'm very excited to not have to convince everybody that massive black hole binaries are exciting Lisa sources, but I will just very quickly talk on the binary evolution life cycle when we have two large galaxies, each with their own massive black holes. When they merge, eventually through dynamical friction, we will bring these black holes closer to the center of the post-remnant galaxy, and in the mass range of galaxies that will host Lisa sources. Typically, these environments will have a reservoir of gas at the center, of which our binary will evolve via interactions with the gaseous accretion disk. These interactions can also vary widely based on our assumptions of the thermodynamics of the accretion disk, also binary parameters. This can change things like timescales and what we expect to see. In our current understanding of binary evolution, I have this figure on the right by Valley et al. From 2024, which has mass ratio on the x-axis, binary eccentricity on the y-axis, and then the black dots on these points are individual hydrodynamic simulations of binaries run by Magdalena Siwek in 2023, and then this color mapping is an interpolation to show which of these binaries are in-spiraling with gaseous accretion torques, and then which of the binaries are out-spiraling. And then also there exists this binary eccentricity equilibrium where you will be either pumped up to larger eccentricities or circularized. This sort of study motivated the initial parameter selection for this project, where we chose a 0.1 mass ratio at an eccentricity of 0.4, as that is a region that has experiences an out-spiral. And then we also compare this to a equal mass binary. Additionally, earlier this year, Alex Dittman published a paper that showed that as we change our assumptions of the disk thermodynamics and simulate thinner and colder accretion disks, this evolution can also change. And so this is just to demonstrate that this is sensitively tied to both the binary parameters and the gas assumptions. On the top panel, we have binary separation evolution as a function of different eccentricities, and then our thinner, colder disks represented by the different symbols, with Mach of 30 being the thinnest disk, which is closer to a realistic AGN disk, but not quite yet. And then in the bottom panel, we have eccentricity evolution as a function of eccentricity. And what we see is with these thinner, more realistic disks, we have a more rapid in-spiral, and also our binaries evolve to higher eccentricities. This is specifically exciting for somebody who's putting relativistic apsidal precession into a simulation because higher eccentricity, smaller separations would mean you have more precessional effects. One more quick example, this is a paper by Madeline Clyburn and Jonathan Drake, also from this year, where they also showed that the evolution of binaries changes sensitively with mass ratio. So this studied just circular binaries, but then varied the mass ratio from equal mass all the way down to 0.05. And what they find is that big plot on the right is all of the different 2D density contours, where we have each row represents a single mass ratio all the way for equal mass at the top and the smallest mass ratio at the bottom. And as you move to the right, again, these are our thinner, colder accretion disks. And what they find in this figure at the bottom left is that the evolution, this y-axis is the dimensionless torque parameter, which if you have a positive dimensionless torque parameter, this is analogous to that out spiral that we saw, negative torque parameter that was analogous to the in spiral. And as we decrease the disk thickness, we see that the torques tend to agree towards in spiral. Except for our lowest mass ratio. And they don't all move towards in spiral at the same kind of monatomic rate. And so there's complex interplay between what's the binary parameter, what's our assumption of the disk parameters. And so I figured, why don't we add one more thing, like a characteristic timescale variation also to the binary's orientation. So in this slide at the bottom left, this is just an n-body movie of what a equal mass binary at an eccentricity of 0.4 would look like at the separations in our simulation, which I'll get to in a bit. And I just wanted to show this because for this talk, I will be defining the binary precessional period as the number of orbits that it takes for the orientation to rotate by pi radians, or essentially for the black holes to switch spots in their orientation at pericenter. So the simulation suite that we have run so far is two mass ratios of 0.1 and equal mass, two different eccentricities of circular, and then a moderately high eccentricity of 0.4. And then for our eccentric runs, we do one where we evolve the binary trajectory on Newtonian orbits, and one where we allow the, include the leading order terms of post-Newtonian, but we neglect the dissipative effects of gravitational wave radiation, which enters at the 2.5 term. To simulate this precession, we have to impose a physical scale. So I've got two movies of our equal mass eccentric and our unequal mass eccentric on the right. And we decide to simulate a total mass binary of 10 to the 7 solar masses at a semi-major axis of 175 Schwarzschild radii, which is roughly a Keplerian orbital period of approximately 23 days. These systems are still sufficiently far from the gravitational wave in-spiral phase where it would take a couple 40,000-ish orbits for the binaries separation to evolve appreciably. And we simulate this with a locally isothermal equation of state, constant new viscosity disk with an aspect ratio of 0.1 or equivalently Mach number of 10. And I just want to point out that some of the things we'll be talking about are the morphology of the gas, like this low density asymmetric cavity, and also the individual mini disks that each of the binary has, each of the black holes. So these are some of our preliminary results. We're still actively running some resolution tests and a couple of different things that we're excited to see, but just to show some of the stuff that we've got so far. We're going to start with the equal mass binary eccentric. And first we're going to want to quantify the cavity morphology, as the binary evolution is sensitively tied to the material that actually makes it into the cavity on these streams. And so from the Santa Barbara code comparison in 2024, there was this nice way to characterize the morphology, the growth of this eccentricity instability that eventually becomes your eccentric cavity, which is just this mass-weighted eccentricity vector on the left. And we can track this throughout all of the orbits of the binary, and then compare how these things change as we include the post-Newtonian precession. So in orange, I have the Newtonian binary, and in blue we have the relativistically precessing binary. Just by eye, what we see is that the 2pn binary has a slightly more eccentric cavity, and it precesses slightly faster than the Newtonian version. I have those roughly signs because we also see that the cavity precession is not a constant rate, it varies with time, and that the precessing binary also has a slightly smaller cavity. And then we can directly look for imprints of this on the accretion rates. So on the right-hand side of this plot, I've got the accretion ratio of M2 to M1 in an equal mass of the same thing, but it just helps us to see how this evolution changes as a function of time in number of Keplerian orbits on the x-axis. First thing that we see for our Newtonian binary is that there is a swapping of the preferential accretion. This preferential accretion swaps roughly on the cavity precession timescale, and then the precessing binary has a very modulated preferential accretion, which is following the full binary, 2 times the binary precession timescale, which is the full 2 pi rotation of the binary orbit. If we break this down into the component accretion rates, this variability of the precessing binary is much more clear in the net accretion rate onto the binary in black. Stan De Laurentiis did a paper on the relativistic equal mass binary that had a really cool analysis of sort of the possible EM signatures that would go with this. But the more unexplored regime is this unequal eccentric mass binary, where we actually exist in a different region of parameter space where the binary no longer precesses. It's actually locked into the phase of the orientation of the cavity no longer precesses. It's locked into phase with the binary. And so we see that our Newtonian binary, which does not precess, has a cavity that stays at a fixed orientation and is pretty eccentric. And then our precessing binary has the orientation of the cavity follows the orientation of the binary. It is less eccentric, and it's smaller than when we had our equal mass binary. Interesting, when we look at the preferential accretion rate again, we see that our precessing binary no longer preferentially accretes. So that's the blue line. This is on an orbit averaged sense, so roughly over a full orbit, there is not consistent preferential accretion onto the secondary, whereas the Newtonian binary has constant preferential accretion over the timescale of the simulation. This is, again, just the component accretion rates, which I'm just going to go past because the accretion ratio showed that. And then one of our last results is this big plot on the right, where we have the binary separation evolution on the x-axis, A dot, and then our eccentricity evolution on the y-axis, which allows us to separate this into 4 different regions of parameter space, where either you are an out-spiraling, getting more eccentric binary, or an in-spiraling, dampening your eccentricity binary. And the main result that we see is in our, again, color code, we have Newtonian binaries in orange, precessing binaries in blue. Our equal mass is that diamond, and then our unequal mass is the circle, both of which seem to move over to this out-spiraling and damping regime of evolution, which we're seeing if that's just an effect of precession, possibly with another selection of maybe 0.5 mass ratio binary. That's one of the runs that we're going to be doing. And this has interesting implications for our eccentric binaries that are in-spiraling, eventually reaching a regime where precession takes over and maybe slows that down. They start to out-spiral and circularize, which would maybe make them eccentric again. And so it's just interesting evolution to look at. And this would maybe have implications for the parameters of the binaries as they enter the Lisa gravitational wave band, specifically with the maybe no longer preferentially accreting and keeping a more unequal mass ratio longer into your evolution, and maybe taking a little bit longer. And so I think I'm pretty much out of time, so this is just a summary of all of the things that I have, and I look forward to questions.
Thank you. That's really interesting. You can lose the preferential accretion. You can line up. We have time for 2 questions.
Thanks for the great talk. I was wondering, when you say gravity, do you mean gravity of the gas or gravity of the binary?
I'm sorry, what was that?
When you say that you have Newtonian versus 2pn gravity, do you mean when you calculate the torque, you calculate the gas torque as 2pn? Is that the idea?
No, just for now, this is the 2pn trajectories of the binary. Yeah.
So you basically, these binaries are fixed, but you force them on a 2pn trajectory?
Yeah.
Okay, and very quick question, do you expect your equilibrium eccentricity to change because of the precession?
I am not too sure yet. Just based on that E dot, it also moved it to circularizing on that last plot. In this one, that's the wrong direction. In this one, it also moved it down to across to flipping the direction. So I guess just based on 2 data points, maybe, but we're looking into it right now.
Maybe you explained this, but could you build my intuition why the 2PN would not have preferential accretion? Like, is there some sort of like cavity structure that?
Yeah, we're definitely, so the streams and the structure definitely gets a little bit more washed out when we look at sort of where in the binary the accretion is happening. This is a plot that I'm currently working about. How do I sort of represent in what phase of the binary is the accretion happening? And so what we have here are these lines are the medium accretion rate onto the secondary of the unequal mass binary as a function of true anomaly, which is just the position of your secondary since last pericenter passage, which allows us to compare sort of the variability in the accretion rates as a function of position. And we see that potentially the binary has just a net different accretion rate based on the amount of gas that's flowing into the cavity, because the cavity morphology has itself changed, and also it's accreting at different phases of the binary's evolution. So we see like larger apocenter accretion, but lower pericenter accretion, which is where a lot of the sort of like stream scooping and stuff happens typically in the non-precessing case.
All right, let's thank our speaker again.
Okay. Hello, everyone. Happy to be here. My name is Ekaterine Dadiani, and today I wanted to talk to you about our work together with Antonella Palmas and others about cosmic pairs. This is a DESI census of dual and offset AGNs as precursors of massive black hole binaries. So we know that galaxies merge, and we know that most of massive galaxies host massive black holes at their center. So in principle, there is a full and so those black holes should also merge. And in principle, there is an evolutionary path that they go through, starting from the galaxy scale separations and then becoming bound binaries and eventually merging and emitting gravitational waves. However, the problem is that in observations, we cannot observe this as like a one sequence. Instead, we see the distinct pieces, each happening on different scales and require different sets of to observe them. So my work is kind of an attempt to combine all of this. Using observations together with simulations and combining spectroscopy with imaging and machine learning to kind of answer this big question: how supermassive black holes merge and how many of them will be detected by LISA. However, today I will just focus on this scale. This is a dual AGN scale, and it's super interesting because this is the phase where both massive black holes are actively accreting, so we can actually observationally find them. However, there has been a statistical census of this are still remain elusive because there is historically there has been a trade-off. So if we have a high-resolution surveys such as HSD and JWSTs, those usually cover only small area, and on the other hand, the wide area surveys lack the resolution. So this is where DESI comes into a play. DESI is a multiplex a spectroscopic survey that has 5,000 fibers, which allows us to get spectroscopy of thousands of targets at the same time. And this allows us to, in DESI data release 1, we already have around 30 million galaxies and 1.6 million quasars. As a comparison, SDSS has in total 3 million galaxies. So among this, we start with finding pairs with the projected separations less than 50 kiloparsec and the ones that are also physically bound with each other. However, we also have the limitation from the survey. This is DESI, because of the DESI fiber size, we limit to avoid blended sources. We limit our minimum cut to be 1.6 arcsecond. Big advantage of DESI is also its multi-tracer strategy. So that means that it at the same time traces different types of galaxies. Starting from at low redshift, we see bright galaxy survey, and then at intermediate regimes, we have large red galaxies and emission line galaxies, and then at high redshift, we have quasars. So this allows us to have this full census across redshift, which is very important. So among those, now we need to define how many or which ones are AGN. For that, we use multi-wavelength, multi-diagnostics approach to not miss anything, including combining emission line diagnostics, most famous BPTs, combining them with 1 MEX, KEX, and then also combining them with the mid-infrared selection, such as WISE colors, and also broadline and quasar identification. So because of this multi-diagnostics approach, we have quite a large census, right? After that, we do a lot of cleaning and refinement, including photometric shredding and also quality of the spectra itself. And more importantly, we also do fiber assignment and completeness correction, including pairwise inverse probability combined with the angular uprating. This is especially important when comparing to the theory. I'm not going to go into details here, but you can read that in the paper also. Right, so this is what we get. So this is our DESI dual AGN sample. Here we show projected separation dependent on redshift, and above we see the histogram distribution of those with the red solid line, and dashed line actually shows the weighted one. To put this into the broader context of dual AGN samples, we compare those with more than 100 literature candidates from more than 100 literature, combining more than 1,000 dual AGN candidates. So the histogram, again, on the above with the black line shows the distribution of those, and also black dashed line also includes the ones that are not spatially resolved, so do not have specific separation distance. They're found with the methods such as double picked emissions, etc. So we already see that DESI actually fills the gaps at several regimes. At the lowest redshifts, it broadly follows already well-sampled by SDSS, and it follow-ups this dual AGN candidates. However, at this regime below 0.2, we have around 500 duals, which is around 6 times larger than the spatially resolved literature points, and 2 times with the, including the ones that are not spectroscopically found. And this part from 0.2 to 0.5 is the one where DESI really dominates. We find 3,400 duals, which is an order of magnitude higher than what has been found before. And then this is the secondary peak overseer we have because of the, again, the tracer change in the DESI sample itself. And then at higher redshift, it gets harder and harder to find the duals in general. However, we find 400 duals, which is 3 times larger than the candidate with the same cut, same minimum angular cut. However, from here, we actually see that at below 1.6 arcsecond, it's actually covered by Cosmos and HSD that we do not find here in DESI. So after this, let's look at where these dual AGNs live. So for that, we look at their host galaxy parameters. Specifically here, we look at specific star formation rate dependent on stellar mass. So in dual AGNs, the one AGN that is hosted by the more massive galaxies, we call those primaries, and we see on the first panel. And the hosted by less massive galaxies, the secondary, and shown on the second panel. And we also compare those with the isolated AGN population on the third panel. So different colors corresponds to the DESI different galaxy types that we mentioned before. And we see that different type of galaxies actually occupy different regions on this plane. We see that quasars and emission line galaxies, green and blue, actually lie near the main sequence, while large red galaxies, the red ones are more massive and constant, while the BGS bright galaxy survey lie intermediate between those two. This lines corresponds to the main sequence at different redshifts, while to the below plots show what is the offset from the main sequence for each host galaxy, and then we group them into these 4 main categories just to make this visualization a little bit easier to read. So what do we see from here? The one thing that we obviously observe is that secondaries actually expand to the lower masses, below 10 to the 9 stellar masses, right? Next thing, and an isolated AGN in mass lie in between those two. The next thing that we see is that secondary actually have the star formation rate enhancement compared to the isolated AGNs. And looking at the below plot, we see that most of our dual AGNs sit either in main sequence or starbus region, while only a little fraction lies in the quiescent one, and that is mainly dominated from the allergies. But what we see here is that there is delta MS enhancement towards dual AGNs comparing to the isolated ones. And especially that is shown in the secondaries. So that is also predicted from that is what we expect, because during the galaxy interactions, we see that gas inflows enhance the star formation rate, and this is what we see here. So this enhancement, then we see how this enhancement changes across the when they come together and together. So we see dependence on the projected separation between the pairs. So let's concentrate on the red one here, red and orange. Those are the dual primary and secondaries, and we see that this asymmetry that I talked about in mass and star formation rate gets enhanced at the closer separation, coming from the tidal stripping and gas inflows, as I mentioned. I'm going to skip comparison with the 1AGNs here, but that is also super interesting to look at, and we need to investigate that more also. So some pretty images. We found very interesting systems, such as, for example, these are some highlights of the high redshift ones. We found around 100 cosmic noon dual AGNs. Also, more importantly for the LISA dwarf AGNs, dwarf duals are the ones that would be in the LISA band. We found around 50 dwarf dual AGNs, and we also compared how many would be actually observed in the LISA band. So let's look at the fraction rates to look at the dual to single rate, how that depends on how that changes across redshift. As I said, each redshift is coming from the different galaxy types. And to compare first to SDSS, it matches with 1 sigma error bar. And then let's compare to the Cosmos Web. We see that ours lie below this, but this is mainly coming from the limitation of different selection limitation, but mostly coming from the fact that they observed highly obscured ones, which is 2 orders of high compared to unobscured ones. And the same goes with the Cosmos sample at redshift high, and then also comparing with Swift, we agree with the 1 sigma. And finally, now that we have this dual AGNs, we're curious how many will actually merge or how many will be discovered by LISA. For that, what we did is we did mock dual AGN catalog using hydrodynamical simulations Adhrit, and we matched the selection criterion of the DESI with that, and then the ones with this mock dual AGN catalog, we fast forward that into time and see how many will actually merge. So on the left, we see this merger fraction, and we see that for DESI dual mergers, this blue one increases as we go to the higher redshifts, and we find that at redshift 1, we already have around 60 to 70%, while DESI dual LISA actually goes lower as we go to the high redshift because of the limitation of the observations that we cannot find the low mass ones at the high redshift, and the LISA it is outside of LISA band. And then on the left, we actually show the rates of duals and also offsets or 1 AGN pairs, how that changes across redshift. And this was only in DR1, but I want to highlight that we're going to do the same thing for full survey, which would have we expect to have more than 4 times larger. I'm going to leave you with this pretty images of some of the duals that we found. Thank you. Oh. sorry, one last thing. The title of the talk is the same as the title of the paper that will be out in a few weeks, so please stay on the lookout for that. I encourage you to see that.
Great. Thank you. We have time for one quick question.
Hi, very interesting talk. So one of the things with dual agents is we don't really have a quantification of how long they are active for. We don't have a quantification of how long they are active for simultaneously, individually, or completely dormant. So when you project your population from the SDSS to Astrid simulation, what are you exactly mapping from those populations to the, if you can.
Yes, so we match exactly like at that redshift how many dual agents are in the simulation at the same time. But I agree that they might not stay AGNs for the whole sequence till the merge, or. But we match with the redshift and luminosity curves and the selection effect, because DESI also has the different galaxy types at different redshifts, right? So we match those separately in Astrid.
Okay, and very quickly on top of that, when you predict the SMBH merger rates for LISA, do you account for the fractions that you might not be seeing and things like that because of this, discrepancy in terms of which are active simultaneously, which are not?
Right. No, we just follow the ones that we mocked, and we just follow those. But I agree that there is a difference between those two. Yes.
Thank you.
Thank you.
All right, let's thank our speaker again.
Hi, I'm Adhrit. I'm a graduate student at the University of Massachusetts at Dartmouth, and I'm excited to talk about a few numerical relativity surrogates that we built over the last couple of years, and by we, I mean my collaborators and I. So eccentricity in particular is an interesting parameter because it contains important astrophysical information about a BVH's formation mechanism and environment, and ignoring it can lead to systematic biases in analysis, and thereby we require accurate models for eccentric systems. And in principle, numerical relativity gives us that, but it's too expensive to directly be used for any data analysis task, and that is where surrogate models come in, which are these models that are trained on sparsely sampled NR data for a parameter space, that once trained can be A, made as accurate as the NR data, and B, can be evaluated at points in the parameter space where there is no NR data. So you can essentially think of them as interpolants for the space of waveforms and the space of remnant properties. So the first of such models that I want to talk about today is the model for the waveform modes themselves, which we call NR-Sur EQ4 no spin. And the algorithm which we use to build surrogate models for waveforms is as follows. We start at a set of input parameters and the corresponding data for it, and the corresponding NR data, I mean. And the first step is to choose which part of the waveform to model, which I'll henceforth refer to as the data piece, which in the case of this example is just the amplitude of the 2-2 mode, which is sparsely sampled in the mass ratio direction, which can also be seen as the blue line in the first plot there. So once the data pieces are chosen, we run a compression algorithm on them called the empirical interpolation, which gives us a basis for a reduced vector space along with the coefficients, which we call the EI coefficients, which also happen to be the values of the data pieces at particular time nodes, or particular times rather. And then the next step is to build interpolants for these EI coefficients as a function of the input parameters, which can then be linearly combined with the EI basis to give us the surrogate model, which can then be evaluated at points that were not in the original training space. So in the plots there, the yellow dots are the EI time nodes in the second figure. In the third figure, the red lines are the parametric fits that we built for these EI coefficients. And in the fourth plot, the black line is the reconstructed data piece, which was not in the original training set. So the eccentric non-spinning parameter space that we're working with was three-dimensional, consisting of the mass ratio, which was between 1 and 4, the eccentricity, which is a parameter which quantifies the degree of deviation from circularity, and the mean anomaly, which is a circular parameter, or a periodic parameter rather, which quantifies the position of an object on an eccentric orbit compared to its periastron, or the point of closest approach. And as for the data pieces of the waveform we model, we expand into a basis of spin-weighted spherical harmonics, thereby decoupling the dependence on source frame angular variables. And then the data pieces end up being the real and imaginary parts of the higher order modes in the co-orbital frame, and for the 2-2 mode, they're just the amplitude and the phase. But there's a problem with using these data pieces directly for eccentric systems, which I'll demonstrate using just the 2-2 mode as an example. So in the plot on the left, in the set of waveforms at the bottom, I freeze the eccentricity to 0 and just vary the mass ratio for a few training samples. And you can see that there are no oscillations in the data set. But in the second set of waveforms there, I now freeze the mass ratio and the eccentricity to a non-zero value while allowing the mean anomaly to vary. And what one can see is that the eccentricity introduces these oscillations at the orbital time scale around the leading order dependence set by the mass ratio. And what the mean anomaly does is it dephases these oscillations in time. And in the third set of waveforms there, I let all the 3 parameters vary randomly. And what I have is an oscillatory mess, which has a direct implication of making the vector space itself less compressible, which therefore requires us to use an inaccessible number of NR waveforms to compress the data set to some required level of accuracy that we want our surrogates to have. But the solution there is, instead of modeling in time directly, we switch to something we call the radial phase domain, which is a special domain in which these orbital timescale oscillations are all aligned. And the way we construct this is by solving the set of quasi-Keplerian equations right there, which is just a system of ODEs that we integrate forward in time. Since those ODEs clearly have Pn terms, this essentially means that this can only be done for a part of the inspiral of the waveform. So what we end up doing is we model a part of the inspiral in the radial phase domain, and we model the merger ring down in the time domain, and then we choose an intelligent way to stitch these evaluations together to give us an evaluation of the data piece for the full time range. And once we do that for the 2-2 mode, we quantify our performance by using by doing a 20-fold cross-validation study. And the performance metric which we use is the mismatch, which essentially is a 2-input functional that quantifies the degree to which the 2 inputs differ from each other. The upshot is a mismatch of 1 indicates that the 2 inputs are as different as they could possibly be in the same vector space, and a mismatch of 0 means that they're exactly the same. And the validation set mismatch errors are plotted in the yellow histogram on the right. In the blue dashed histogram, we plot something different, which we call the NR error, which is the mismatch computed between the highest available resolution of NR available to us against the second highest resolution. And those 2 histograms being comparable indicates that our model is as accurate as the underlying simulations themselves. And on the right, I have a typical evaluation in the validation set of the 2-2 mode. And it's clear that the surrogate's evaluation is faithful to the underlying data. And this approach follows over naturally to the higher order modes as well, as can be seen from the same observation for the mismatch histograms on the left and typical validation set evaluations on the right for a few of the data pieces for the higher order modes. So the next surrogate that I want to talk about is the remnant surrogate, which is a surrogate for the remnant mass, spin, and kick as a function of the input parameters. Remnant models are important in simulating black hole populations in various astrophysical environments, simulating hierarchical mergers, quantifying quasi-normal modes, and also building backwards one-body models. And what we call the remnant surrogate is essentially just a GPR fit, or a Gaussian process regression fit, for these aforementioned quantities as a function of the input parameters. And we work with the exact same parameter space as before. But additionally, we run Cauchy characteristic evolution on each of those simulations that we used for the waveform to compute the strain and the Weil scalars, which we use to then compute the Poincare charges, which we then use to compute the remnant mass, spin, and kick. And in the 4 plots, I plot these quantities, where the x-axis is the mass ratio, the color of each marker is the eccentricity for that particular simulation, and the direction or the angle of the arrow marker with respect to the x-axis is the mean anomaly. The upshot is that the mass ratio still sets the leading order dependence, and the eccentricity and anomaly parameters essentially are subdominant effects around that leading order behavior. So once the GPR fit is built, we again quantify performance by doing a 20-fold cross-validation study, and these errors are plotted in the orange histogram there. And we again compare with NR errors and find that our model is again as accurate as the underlying simulations themselves. We do an additional test here where we also compute the errors that are accrued by using a quasi-circular waveform, a quasi-circular remnant model to approximate eccentric remnant quantities. And those errors are plotted in the purple the purple dotted histogram, and that histogram lying to the right of either of the earlier two histograms indicates that it's probably not the best idea to ignore eccentric parameters while modeling such systems. Finally, in the last few years, a couple of groups across the community have quoted these oscillations in remnant quantities as a function of eccentricity as they define it. And in the left plot here, we evaluate our model at a fixed mass ratio while varying the eccentricity and mean anomaly according to the two paths on the mean anomaly eccentricity subspace in the plot on the right. And we find that we reproduce these oscillations when we follow the non-trivial spiral path across the anomaly eccentricity subspace. Whereas if we just freeze the anomaly and vary the eccentricity, we essentially just get a monotonic increase in the value of the remnant mass. The upshot here is that the oscillations that the other groups have been seeing are likely due to them ignoring the parameter of mean anomaly altogether. And the idea is that to model any eccentric system, two parameters are necessary. So one can't ignore one parameter. And finally, the third surrogate model that we built was a dynamic surrogate model, which was for the eccentricity and the anomaly as functions of time. And these models are useful when, in case one wants to reparameterize an existing eccentric model to other eccentricities and anomalies in time. And the other use case is this niche thing, which we call local parametric fitting for waveform surrogates, which is using local values of these parameters as opposed to the global values to build the parametric fits from the flowchart on a few slides ago. So again, we start at the same parameter space, and this time the quantities that or the databases that we model are the mean anomaly as a function of time and the eccentricity as a function of time, which are given in the third and the fourth plots on the right. And using the same approach as was used for the waveform, and again doing a k-fold cross-validation study and then computing errors and NR errors and then comparing them, one can see that this model is also as accurate as the underlying simulations themselves. And on the right, I have a plot of the worst case evaluation for the eccentricity and the anomaly. And even the worst case evaluation looks faithful to the underlying data. So just to summarize, I presented results on 3 models that are valid in that particular parameter space right there. And some like obvious extensions of this work are including align spins in addition to eccentricity, including, hybridizing the early inspiral with PN for the waveform surrogate, also potentially including environmental effects in case this model were to be used for an SMBH merger. And these models should be available in public packages, namely SurfNBH and GW surrogates soon enough. And on the right, I have QRs for 2 out of the 3 papers that are out on this work, and the third one should follow soon. So thanks for your time and attention. I'll be happy to answer questions.
Thank you. Questions?
Thank you for the very nice talk. I would like to ask you, could you remind or could you explain why do you need to extend from 0 to 2 pi and add these buffer zones for the mean anomaly?
Oh, sure. Yeah, so we expect any quantity that we model against the mean anomaly to be periodic in the mean anomaly, which means that it should give the same result at 0 and 2 pi. But given that we don't have simulations exactly at 0 and 2 pi, there is no way for the model to learn this periodicity. The way we force the model to learn this periodicity is by artificially augmenting data beyond these boundaries, which is using the data within the boundaries and copying them over beyond the boundaries in some way, which is different for the remnant parameters and the waveforms. And in doing that, the surrogate then learns the periodic nature at 0 and 2 pi. So it is essentially just used to ensure that the value, the evaluation of the surrogate at 0 and 2 pi is exactly the same, which is something we would expect from the underlying data.
Okay, great. Let's thank our speaker again and call up.
All right. Hello, everybody. I'm Alberto Magaraggia. I'm a third-year graduate student at the University of Miami. And today, I'd like to discuss how LISA can probe one of the most intriguing possibilities in cosmology, which is the existence of primordial black holes. So, what are primordial black holes? Well, primordial black holes are black holes that form in the very early universe, soon after the Big Bang, from the collapse of overdense regions. We can see here a schematic representation of the process. So density fluctuations could grow larger than a critical threshold. This, on its own, it's not sufficient to create a PVH. A primordial black hole is formed when the fluctuation re-enters the horizon. And hence, PVH formation is epoch dependent, because larger scale modes re-enter later, and so we can form more massive primordial black holes later in time. Why do we care about primordial black holes? Well, they're exceptional dark matter candidates. They fulfill all the characteristics that dark matter has, but most importantly, they don't require new physics. Big plus. Also, they could be the seeds of the supermassive black holes. So here we can see the PVH constraints on the abundance. So on the y-axis, FPVH, the ratio of the energy density in PVHs to the one of the dark matter. The colors here are the constraints, and the white areas of the plot is where PVHs can still be a thing, still exist. For example, here they can be the totality of the dark matter, while here just the 10% of it. Big caveat, all of these constraints assume monochromatic PVH mass functions, so they're technically just useful for monochromatic mass functions. When we have an extended mass functions, these constraints are not really exact. They have to be recomputed, and so usually they're more relaxed when we have an extended mass function. Having said that, here in blue, I present you our proposed PVH mass function. And you can see that it's feasible. I mean, it crosses some of the constraints, but mainly it lies below. But again, the constraints are monochromatic. So the nice thing is that we can relate the early universe physics with primordial black holes. So the phase transitions enhance PVH formation, and those are the peaks of our mass function. Moreover, as you can see, it is a very extended mass function. It ranges from the asteroidal range to the supermassive black hole range. Now, we talked about PVH as single objects, but why not talking about binaries? So we have two formation channels, one in the early universe when two primordial black holes decouple from the Hubble flow. They usually avoid head-on collision, and they form eccentric binaries. They emit gravitational waves and they eventually merge. Or, in the late universe, after structure formation inside the halo, they have a close encounter, and so they form a bond system. And also, those emit gravitational wave and eventually merge. These two channels can, in principle, coexist. However, we think that the early formation channel is dominant for the very early universe, and the late formation channel is dominant for the local universe instead. Now, we can test primordial black holes in the low mass regime with LBK, LIGO Virgo Cagra, and this was a trigger event from the collaboration, so a candidate event on November 12, 2025. Why is this interesting? Well, it has a chirp mass between 0.1 and 0.87 solar masses, meaning that at least one of the two is subsolar. So since we don't have any mechanisms to form black holes that small, well, that could be the first primordial black hole detected, pending, of course, confirmation about the event. So, as a motivation, we use that candidate event to test our mass function and predict how many mergers should LBK see. So with our mass function and the late merger rate, because LBK probes the local universe, we try to see how many of these things LBK sees. And here you can see the M1, M2 planes, so the two component masses, and the color code is the merger rate as seen by LBK. We can see there's a region where the rate is maximized, but the nice thing is that the cumulative predicted merger rate in that area of the plot is 0.8 events per year. which is more or less the same rate as one event in 4.35 years. That's the time LBK was operational. Current LBK data seems compatible with our mass function and possibly with a PVH origin for that candidate event. Now, moving on to the very massive end of our mass function, let's talk about supermassive black holes. Well, supermassive black holes are black holes with masses greater than 10 to the 6 solar masses. The key question in astrophysics is how do we get there? How can we form 10 to the 9 solar masses black holes at redshift 6? Well, we have three scenarios. One, the light astrophysical seed scenario, where we have about 3 remnants. So we start from black holes of around 100 solar masses, and through sustained accretion and mergers, they can grow up to the 10 to the 9 solar masses objects. Or we have heavy astrophysical seeds, so direct collapsed black holes, a cloud gas gets directly collapses into a black hole. So starting from 10 to the 4, 10 to the 6 solar masses, it grows up to the 10 to the 9 solar masses. These are called astrophysical seeds, and they usually invoke Eddington or super Eddington accretion rates. So they start from redshift 25, and they accrete at the maximum rate that black holes can grow for most of it in their life, basically. To relax a bit those accretion constraints, we can think about a third option that are primordial black hole seeds. So we have seen that our mass function can already populate those 10 to the 3, 10 to the 8 solar massive range. And how can we distinguish between the three? Well, we can check the redshift distribution of the mergers, because we expect the astrophysical seed scenarios to produce mergers after redshift maybe 20, while if we get mergers at very, very high redshift, those could be the primordial black holes. So that's why LISA is extremely important. Here is just a summary of what I just told you. So on the y-axis, the total mass of the binary as a function of the redshift. So if we see mergers between redshift 0 and 20, well, all of those could be all those primordial black holes or astrophysical could produce those mergers. But if we focus on redshift greater than 20 or even greater than 30, those could probably just primordial black holes. So if we see mergers at those high redshift, that could be a smoking gun of primordial black holes, and hence also dark matter. So, as we did with LBK, we did also with LISA. So we tested our mass function in the high mass regime. We used the early merger rate because, of course, LISA probes the very high redshift regime. And this is the result. So again, the M1, M2 plane, we can see that the rate, as seen by LISA, is maximized for binaries between, with masses between 10 to the 3 and 10 to the 4 solar masses. And as a summary of our results, we can see this table here. So when the total mass of the binary is between 10 to the 3 and 10 to the 4 solar masses, we have a few events per year, almost regardless of redshift. So we can see, in principle, mergers at extremely high redshift, so even redshift between 35 and 50, while when we increase the masses of the binaries, the rates drop out. So the key question, actually the key result here is that we do predict few events per year for redshift greater than 20. So if primordial black holes are there, LISA will see them. So that could be a possible answer to what seeds the supermassive black holes and also dark matter. So, primordial black holes offer a unified framework, so we can explain at the same time the dark matter and the supermassive black hole seeds. And we tested our physically motivated mass function. Remember that it's extended, so it can avoid the constraints. And we tested it in the low mass regime with LBK data. It seems compatible. We also made some predictions with LISA. And so we know that gravitational waves are the big test for primordial black holes. And so LISA can discriminate the light and heavy seeds from the primordial black hole seeds, and possibly, possibly in 10 years, maybe 15, we can actually have a clear answer on what seeds the supermassive black holes and also dark matter. And thank you.
Thank you very much. Questions?
How likely do you personally believe that we will find...
Sorry. Again, because I couldn't hear you.
Oh, how likely do you personally believe that we'll find primordial black holes using LISA?
I do believe in primordial black holes. I mean, I think it's they're nice candidates because I don't know, Occam's razor. They can explain many things at the same time. So there are some caveats in the model. So of course, the mass function. I mean, it's uncertain. I mean, we tried to tie the early universe physics with the mass function, but I mean, we don't have a clear view of the early universe to create that mass function, so it's a tentative mass function. Also, the rates are extremely uncertain. That's the best we can do right now, so I really hope we will get some mergers at extremely high redshift, and if we get those, that would be amazing.
Thank you.
Hey, thank you for the talk. So my question involves if at those mass ranges for PBHs around like 10 to the 14 or 16 grams, we expect our Hawking radiation to be kind of hot as well. Do you think that would affect dynamics or things that would impact like merger rates as well, especially if they're happening in like some background matter or whatnot after that hot?
I don't think the merger rate is sensitive to those things, especially because, at least for the early channel, they're isolated system, and I don't think they take into account that. And I'm not sure how much that would affect. But I don't think the merger rate are sensitive to that. But that's
thank you.
That's true.
All right, let's thank our speaker again. All right, last talk of the day.
We made it. So I know we've been through a long day, so I will keep this math light. My name is Emily McPike, and I am a recently graduated master's student. Thank you. Incoming PhD student at the CUNY Graduate Center. I study electromagnetic counterparts to binary black hole mergers and active galactic nuclei. So you may wonder, why am I in the massive black holes section? And my answer is there's a massive black hole right there. I am your friendly next door neighbor, here to ask you for a cup of sugar and to get excited with me about a promising multi-band, multi-messenger source accessible to us with LISA. So most of the heavy lifting for my introduction has thankfully been done for me already. On the left, I have an example of an active galactic nucleus, or AGN, hosting galaxy, with an inset to the right displaying the zoomed-in nucleus. In the presence of this accretion disk, nuclear star cluster objects like stars, and for the purpose of my talk today, stellar mass black holes, can become captured in the disk over time via gas dampening and dynamical cooling. While embedded in this disk, these black holes can migrate and find other black holes in the disk, pairing up to form a binary black hole system, which can evolve to merge. With our current ground-based gravitational wave detector network, we've been able to detect hundreds of binary black hole mergers. We know that not all of these events should originate within these AGN disks, but we don't know what that exact fraction is. Increasingly, though, we're seeing evidence that this fraction is non-zero, especially with the most recently released Gravitational Wave Transient Catalog 5, which we have found an emerging high-spin, high-mass population that we may be able to attribute to this AGN channel. So LBK is giving us early constraints on this AGN channel, but LISA stands to unlock a whole new world of astrophysics related to the AGN channel. LISA will be an unprecedented probe into wet MREs, light EMREs, and even the early in-spiral of stellar mass or smaller black holes. So where we are now is if we are able to detect a multi-band source originating within an AGN disk, we will receive an unprecedented probe of actually environmental impacts on waveforms, allowing us to open a whole new box of interesting physical questions. And this in and of itself is a unique environment to study binary black hole formation in. It's practically the only environment where the binary black hole will essentially always merge within a dense bed of gas. So the remnant black hole will always have the chance to interact with the surrounding matter. Here I have a cartoon of two post-merger scenarios, one in which the remnant black hole injects luminous shocks within the disk, possibly injecting turbulence, and in the case of a low luminosity AGN, possibly inducing a brightening event. And the second scenario where the remnant black hole ignites a jet. The second scenario I'll explore today. Here I have a 3D simulation of a remnant black hole driving a jet, which will look familiar to somebody here in the audience today. And if this jet breaks out of the disk, it will induce a flare, an electromagnetic counterpart to the gravitational wave signals. This multi-band, multi-messenger event combined would be an unparalleled probe of accretion physics and strong gravity and even cosmology. But the challenge to detect that confident flare is one that's complex and really confusing. So, for one, it's a complicated problem. We have not yet found that flare. And it's a little bit because it's like finding a needle within a haystack. Here I have an example AGN light curve to remind us all that AGN are well known to be intrinsically variable. So we're looking for a flare in something that loves to flare. And additionally, we know that AGN outshine entire galaxies. So the flare needs to be brighter than that in order to be detectable. And on top of that, gravitational wave localization volumes can span huge swaths of sky containing millions of AGN. So how do you pick out an exotic flare among all of that noise? So luckily for us, we're 10 years out to LISA and maybe half a year out from IR1. So to understand the governing physics behind these flares and when and where to point our telescopes when chasing these events, we need to use the power of computer simulations to strip away the haystack and focus on the needle. It's important for us to constrain what characteristics of the nuclear star cluster and AGN influence bright electromagnetic counterpart production. To answer this question, we use the Monte Carlo for AGN Channel Testing and Simulations, or McFACS, software. Feed McFACS information about a nuclear star cluster and AGN, and it will output to you all of the resulting AGN channel binary black hole mergers in your simulated universe. McFACS is built as a sandbox, so you can use that output to go back to your input and refine the knobs until your output reflects the universe that we live in. This is an example of a default output for McPike. Here is the remnant mass, along with the remnant spin, both here as a function of radius. Color in these diagrams represents merger generation, where gold represents black holes that are undergoing their first merger, purple their second, and red so forth. The black hole spin is the jet's energy source, and the black hole mass will determine how much mass can get onto the black hole and funneled into the jet. With this, we can make a model for how bright a jet would be. This is the resulting jet luminosity as a function of radius in the disk for a Serco-Goodman disk model. I have the disk density profile plotted atop of the bottom panel. Here, color still represents merger generation, but I've grayed out unobservable mergers. Mergers that have jets that are both dimmer than the bolometric luminosity of the AGN and fail to break out of the AGN disk before the jet turns off. Notice that the brightest mergers that break out the brightest jets that break out are biased towards the inner disk, the thinnest, densest part of the disk. Mergers in Serco-Goodman-like disks are highly efficient because of that dense, thin nature. But we know that not all AGN are exactly alike. So we can extend this analysis to a variety of choices within the nuclear star cluster, so the red highlighted panels, and AGN, the blue highlighted panels, parameter spaces. When we did this, we were also able to bin all of our simulated mergers by chirp mass, Grace DB-like chirp mass bins specifically. And with this, we can determine how likely any given merger detected by LVK is to produce an observable electromagnetic counterpart. When doing this, we found that two parameters consistently produced bright electromagnetic counterparts, that being heavier seed black holes, so more top-heavy IMFs, and longer disk lifetimes promoted the chain of hierarchical mergers, promoted the formation of high-mass, high-spin mergers capable of driving bright, prompt jets. We then extended this model to a Thomson-Quadrant-Murray TQM disk model. This is a less dense disk model, and here I've plotted this disk model's density profile atop the resultant jet luminosities as a function of radius. With this disk model, we found that overall, given the less dense nature of the TQM disk, the overall merger rate was significantly decreased because of those lower densities. And as a consequence, those high mass, high spin mergers were inefficient at forming, and thus the cadence of bright electromagnetic counterparts were also reduced. Now, directly compared together, what I should leave you with, I'm not done yet. So, sorry, I know we're all excited to get to dinner, but despite my slight misspeak, what I'm showing you this here, and an important note to mention, is that while it's not directly apparent here, the gravitational wave rates that result from these two different disk model choices are significantly different. The Serco-Goodman disk results in a default Serco-Goodman disk within the McPike model, results in a gravitational wave rate of about 11 mergers per year per cubic gigaparsec, while the TQM model results in a rate of about 1 merger per year per cubic gigaparsec. It's a little bit of a tongue twister. So that decreased density within the TQM disk model overall leads to less mergers. But now we can return to the likelihoods that are presented here in front of you. The likelihoods I've shown you don't yet include observational effects. And in reality, we should expect about half of these mergers to be kicked away from us, and we find about half of AGN are oriented face onto us, obscuring our view of any flare. So this means we'll end up losing about 3/4 of all of these events. And so regardless of disk model, we found that only about 1% of all binary black hole mergers may have optical counterparts if we only attribute that high mass, high spin subpopulation found in the recent GWTC catalog to the AGN channel. We also use the observational impacts and methods used here to determine this percent. And so 1% is low, but it's not nothing. And so while we may have to get lucky, we have no idea what Lisa will be able to help us probe for this interesting and exciting multi-messenger source. If you'd like to know more about our methods and our future work, please feel free to take a picture and check out our recent paper, McFacts 4. And we're planning to extend the capabilities of McFacts to also predict multi-messenger predictions for emeries and emeries. And if you're excited to learn more about McFacts, please come see our other group members here as well. Miranda McCarthy, Jake Postiglione, and Sean Ray all have posters in poster session 3. Feel free to come talk to any of us at any time this week to learn more about McFacts and the power of the AGN channel. So with that, please check out McFacts, and thank you.
Thank you. Any questions? Everyone's just McHungry.
I'm ready to get to dinner.
Okay, with that, we did it. Enjoy your evening.